All right, cool. So, actually, let me grab our checklist, tell you guys where these questions are fitting in our to-do list. Okay. So, we are looking at number 2 on our checklist. Identify and explain isomers, and there are 3 different types. There are the structural isomers, the geometric isomers, and also the enantiomers, also known as optical isomers. So we're looking at this one today. Keep going. You guys ready? You're looking for things. What paper? What do you want? Thursday and Friday. Let's see. Isaiah, the notes would be in that binder over there. Can you get the piece of paper? I gave you guys this. Wait, these are my copies. Yeah, it'll be in the binder. I don't think I have any of them anymore.
The chickens? Same word, birds right here.
I look for the things that I would have handed out.
I have my movie.
Pause this. All right. Can I start now? You guys ready? I put all those on there because those are all things that I've handed out that you're going to find useful. All right. So we're looking at number 2 of our checklist. Yeah. Looking at our isomers. I just want to remind you guys that we have talked about isomers before. So if you guys remember with organic chemistry, lesson number 5 and lesson number 6 both talked about isomers. I recommend you go back to those 2 if you want any refresher on it. But you should hopefully be pretty confident with structural isomers because it was more or less what the spec internal was all about. But I still want to revise your memory and also talk about the other 2 as well. So, just to remind you guys, when we talked about structural isomers, we talked about stuff that had the same formula but different bonding. So, for example, if I was to choose C4H times 2 is 8, 9, 10. Oh, like this is an example of my, come on, focus. All right. Ready? Okay. Shh. All right, so this is an example of a formula, and there's multiple different ways that I could arrange those atoms. I could, for example, have 4 carbons in a row, the alcohol on the end. I could also, come on. So that's one version of my molecule. I could also move the alcohol down onto carbon number 2. Again, both of these have the same, come on, focus. The same formula, but different arrangements. So the OH is on a different alcohol, sorry, on a different carbon. I could also move the carbons around as well. So I could have maybe like a 3-carbon chain with a branch coming off of it, like that. So all of those would be examples of structural isomers of each other. All I've done is I've changed the bonding pattern. Cool. And just as a refresher, because it's important in case it does come up on the exam, we refer to these as, like, for example, this one would be a primary, secondary, and tertiary. And that's referring to looking at the carbon that the alcohol is on. How many carbons is it attached to? So this guy's attached to only 1. This guy here is attached to 2. And this guy here is attached to 1, 2, and 3. So that's where I'm getting the primary, secondary, and tertiary from. Nice little refresher. Are you okay with that? Okay. So that was one type of isomer that we talked about, and we talked about it quite a bit because, like I said, in spec, we were looking at that as our idea. The second type of isomer is known as a geometric isomer. So we're talking about geometry now. Now, some things to remember with geometric isomers is they only occur in the alkene. So basically, I need something with a double bond. The reason why I need something with a double bond is because when it has that double bond, the molecule cannot rotate. So for example, I have an organic molecule here. I'm just going to try to move it so that way not too badly over the notes. Right now I have a diol because you can see I have an OH, OH, and then hydrogen, hydrogen, carbon, and then my single bond here. So if we were doing this, if you guys remember, I'm not fussed if you draw it with the OHs both on top or if one OH is on the bottom and the other one's on top because this molecule can rotate around. Yeah? If, however, I take off 2 hydrogens, so I'm removing those 2 hydrogens, and I form a double bond, like that. Come on, get in. What now happens is I cannot rotate this molecule around. So it matters where these oxygens, or sorry, I should say the alcohols are located. Yeah? So cannot rotate it. So if I was to do a molecule like that, I would, for example, have 2 options. I could have C double bond C with the OHs on the top and my hydrogens on the bottom. Or I could have it so that way I have 1 OH on the top and the other OH on the bottom. So that's what that would look like. So in this example, I have my OHs on the top. The other example, and I would have to break the bonds, would be like that. So I would physically need to break the bonds in order to make that new molecule because this guy cannot rotate to do that. So what we refer to these is this one, when they are on the same side, is called cis. And this one, when they're on opposite sides, is trans. Mm-hmm. So cis, I like to think about as same. They're on the same side. And trans, I like to think about transfer to the other side. You can talk about transgender as well. That's another change. Yeah. All right. We okay with that so far? Yep. All right. The other thing to keep in mind with these geometric isomers is that this only happens if each of the carbons involved in the double bond have 2 different things attached to it. And let me show you what I mean. So for example, if I had C double bond C and I still had that OH and an H, if this guy over here had two hydrogens, then that's a carbon that has two of the same things on there. So this would prevent it from making cis-trans isomers. Whereas this one still has two different ones. So both of the carbons involved need to have two different things. So this one would have no geometric isomers. Yeah. And if I was going to name either of those two, I would say this one is trans what is that? 1, 2. Oh wait. Trans 1, 2 dihydroxyl ethene. If I was to name that, this one would be cis 1, 2 dihydroxyl ethene. So all I do is I name it just as I would. I just stick the cis or trans in front. Cool. All right, next idea? Not yet. Still writing. No, I'll move that down. There you go. X is showing that this guy here cannot form cis-trans isomers because you see how this carbon has two of the same thing, two hydrogens. No. Two of the same attachment. So two hydrogens. Whereas this one would actually meet the requirements because it has two different things on there. But both of those carbons need to have two different things. If both of them don't have two different things, then no geometric isomers. Whereas this guy up here does have two different things. This guy has two different things. And it doesn't need to be the same two different things. I could also have things that are like I could also have something like this, and this would form cis-trans isomers. And I could have longer chains of organic molecules. So I could have longer chains of it. So long as each of the carbons involved in the double bond have two different things attached, it's fine. These I would call a trans because you see how the CH3s are on opposite sides. Yeah, this one I would call a cis because it has it on the same side. All right, can I move it? No. I'm going to show you guys, and then I'll talk about optical isomers. My hydrogen. The reason why it's important to know that is because when you get your isomer question, they might use it as a distinguishing factor, being like, oh, this one is an alkene but doesn't form geometric isomers. You need to know what that means. Because that'll help influence where you then place the double bond. Okay, move it now. Cool. The last one I need to talk about is optical isomers. With the optical isomers, they are referred to by several different names. You might hear them being referred to as enantiomers. You might also hear it being referred to as stereoisomers. I just want you guys to be aware of the different terminologies they might use. But mostly they're pretty good about it on the stereoisomers. That's other ways they might call an optical isomer. More likely, they will use both terminologies. So that way, like if they use the word enantiomer and you don't know what the word enantiomer is, they usually have optical isomer in brackets. But I want to point it out in case they forget to do that. All right. Optical isomers are atoms, or sorry, I should say molecules that are mirror images of each other. So, for example, I could have something that is a carbon. I'm going to put this guy down here. So this guy here has 4 different things attached to it. It has coming out of the plane towards me is a hydrogen. Going behind the plane over here, actually I should say within the, no, that's behind the plane. Behind the plane, I have a chlorine. Above, I have a OH, and then on this side, I also have a nitrogen, like that. That's the 3 dimensions of this molecule. Do you want me to explain again? Okay. The triangle means that this is coming out towards me. The straight lines refer it's within the plane. So if my paper was the plane, it's within the plane. And then the dashed lines tells me that it's behind the plane. It's like going into the ground. It's just a way for me to communicate 3 dimensions. Yeah. 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 Okay. You understand that? All right. So this is one of my isomers. And what I could have is a mirror image of it. So a mirror image of it would look like, I'm just got to get in the right position, like that. So these are mirror images like your hand. Yeah? And the thing to remember about these optical isomers is that there's no way I can rotate this molecule in order to make it the exact same molecule. That's why it's a mirror. So like, for example, with my hands, there's no way I can rotate my hand around to get this hand to look like my left hand. Yeah, because even if I have it like this, my palms are meeting each other. It's not like I have my hand with my thumb on that side. Yeah. So like, there's no way I can move these molecules around, because if I try to line it up so that way it's like, oh, I want to line it up like that. And now I have these 2 in the right place, but now the chlorine is coming out and the hydrogen's going behind, whereas the hydrogen's coming out and the chlorine's going behind. And there's no way I can rotate this molecule in order to get it to be the same molecule as this guy. So they're mirror images. So if I was to draw that mirror image, what I would be showing is the exact same molecule, just written backwards. So those are mirror images of each other. Now, in order for me to do that, I need something called a chiral carbon. And a chiral carbon just has 4 different things attached to it. If I didn't have 4 different things attached to it, it wouldn't form mirror images, because then I could rotate it. Yeah, we're talking in 3 dimensions. All right. So like, for example, if I got rid of the nitrogens, say the amines, Yeah. So this is an example of a molecule that will not form optical isomers because it has 2 hydrogens attached to it. And this guy, if I rotate it, I can't actually get it to be the same molecule. So this one's not going to form mirror images. Can you see how I rotated it and now it's the same molecule? So it needs to have 4 different things like that. Once it has 4 different things, then it can do it. All right. Some things to keep in mind when you are explaining what we are talking about with optical isomers is that you need to explain that they are mirror images of each other. And because they are mirror images, they cannot be superimposed.
Yes.
So basically what that means is I can't lay them over in any method that's going to allow them to be the same molecule. The other thing they often ask with this is then how do you figure out which molecule is which? And the way you distinguish is by plain polarized light. These guys rotate in opposite directions. So one rotates clockwise and the other one rotates counterclockwise. So it means that there's like no way for me to lay them on top of each other and they form the same molecule. So these molecules, interestingly enough, so what's interesting about these molecules is that they will have exactly the same properties when it comes to melting point, boiling point, and things like that. The only way you can tell them apart is by using that polarized light and seeing how they rotate. What is really neat, though, about these two guys is that they can have completely different medical and like chemical properties in a sense of like chemical reactions. So if you guys have taken bio, you would have learned that we have 22 amino acids. And most of those amino acids will form optical isomers, and our body only uses one form of the amino acid, which is really cool. I think they only use the L form, which I can't remember if it's clockwise or anti-clockwise. The other thing is when it comes to a lot of our drugs that we develop and make, this could be a factor in whether or not the drug works. And there has been instances where the optical isomer version of the drug is actually toxic, whereas the other version is our medical drug. So just an interesting fact about optical isomers that it does play an important part with chemical reactions, but property-wise, melting point, boiling point, they'll have the exact same profile. All right, so let's talk about the checklist and what we've covered so far. That's basically the end of the notes for you guys. So we have looked at the isomers. So if you can identify some of those isomer features, that's going to be enough for an achieved. We also actually talked about function groups and names. If you can identify all isomers or some isomers with a partial justification. So when you guys see these questions, if you can answer some of them but not all of them, that's basically going to get you to the merit level. And the excellence will get you all the way through where you can identify all of them. Let me show you what they mean by this question, so that way you guys know what you're looking for. So if you guys remember back when we did this last term, and very early in last term, there were these collated questions about structural isomers that I gave you guys. And with those questions, I did adapt it, that's right. You were given a formula, and then you were given descriptions of what the molecule is based on how they reacted. So for an achieved, you basically identify one of these molecules. For the merit, it usually was about half of them or maybe 3 of them. And then for the excellence, you got all of them. So no written explanation, just figure out what the molecule is. So very similar to kind of spec work. Yeah, this is for the external. So it's very puzzle-like. So that's what they mean by some or all of the molecules. And like I said, this is why I said this is easier as an excellence kind of exam, because you just need to figure out what it is. You don't have to actually write any justification to it, which is nice. That was that there. And then I wanted to show you this checklist. So if you guys remember, this is the audit of all the questions that they have on the past exams and when they've come up. As you guys can see, the optical isomer question comes up every single year. So that's a really easy question to get. And the good news is being able to draw both of those anemometers, so being able to do this, is usually a merit point. It's really ridiculous how much they give you for that. Usually they have a justification, but the justification is really easy. It's just this. Cool. We talked about how we distinguish them. That's about the polarized light. The be able to draw structural isomers. This one comes up every couple of years. It's not always consistent when it does come up. And then classification, I talked about at the beginning. Again, a useful thing to just know what it is in case it does come up. It hasn't come up in a very long time, but it might come up in the structure of the question. So just kind of keep that in mind. All right, so let's go back to the lesson that we are on for organic to show you guys what your options are work-wise. Did I? Yes, I did. All right. Cool. So, I want to play some last person standing with you. That's right. We'll do that. Yeah, let's do that first.